Starting from rest at point a 50 kilogram person swings along the circular arc over a lake over to point D, where point D is the same height as point A. The distance from the where the person is to where the rope is attached is 6.4 meters. And we're going to ignore air resistance and the mass and the elasticity of the rope. And we're going to look at the person swinging 3 times, each time letting go of the rope at a different point. So in part A, on the first swing, the person lets go of the rope when arriving at point B. So since point B is at the bottom of the path, they will be moving horizontally at that point. So when they leave the rope, they're still moving horizontally, and they're going to end up in a state of projectile motion. So it looks kind of like that. In part 2, they're going to let go of the rope when they get to point C. So C, they're still moving, and they have a bit of an upward motion, but they're not moving as fast. So it'll be something that looks kind of upward and a little bit steeper downward like that. And the one that people tend to mess up is D. Because on D, they let go of the rope at, in part 3, they let go of the rope at point D. But at point D, they are the same height that they started with, which means they have all of their gravitational energy they started with is now all back to gravitational energy. There's no more kinetic energy. So at point D, they're at rest. So if they're at rest and let go, they're just going to drop straight down into the water. There's going to be no projectile motion trajectory. It's just like straight free fall, vertical free fall. In part B, for the person-Earth system, is the mechanical energy conserved as the person's center of mass moves from point A to point B? Well, since we're considering the person and the Earth, we can include gravitational energy, and as they move from point A to point B, the only non-conservative force acting on them is the tension in the rope, but that is perpendicular to the motion at the entire time, so that does not do any work on them. So the only other force in this system is gravity, and gravity is a conservative force, so the mechanical energy is conserved as it goes from point A to point B. But in part C, if we're looking at just the person and not the person-Earth system, then the mechanical energy would not be conserved because, and if you look back at the last page of Notes 9 on conservation of energy, we did a couple examples of this. When you just are taking into account the person and not the Earth, you cannot have gravitational energy, because if there's no Earth, that means there's no gravitational field that the person's in, so there's no gravitational energy. So the person starts off with 0 energy, because the only energy they could have is kinetic, and they have nothing, and then down at part B, they suddenly have kinetic energy. So energy is not conserved, because this external force of gravity is doing work on the system to increase energy from 0 to something down at the bottom. And parts D and E, we get into the math part of the problem. So part D, the center of mass of the person on the platform is 4.1 meters above the surface of the water. So I'll label that in the diagram. From here to here is 4.1 meters. Point B is 2.4 meters above the surface of the water, which means the height difference between A and B would just be the difference between those two numbers. 4.1 minus 2.4 is 1.7 meters. So we said that if we set up conservation of energy, which we said back in part B, we can turn the initial gravitational energy into a final kinetic energy. Because with the conservation of energy formula, the person has no initial kinetic energy, and if we take the lowest point of the path to be the 0 point, there's no final gravitational energy. Now you could make the argument that there is gravitational energy because they're above the surface of the water, but there's gravitational energy here also. So you could have both an initial and a final gravitational energy, but the problem becomes much simpler if you just set this as the 0 point, and then say point A is a height of 1.7 meters above point B for the initial gravitational energy. So we're going to have mgh equals 1/2 mv squared. Cancel the m's from both sides. Solve it for v. Remember that g is equal to the 1.7 meters. And you'll get an answer for v of about 8.2 meters per second. So at point B, if they are moving horizontally with a speed of 8.2 meters per second, in part E, you want to figure out the horizontal distance moved from where the person releases the rope to when they land in the water, which is basically this distance right here, labeled with this green arrow. So this is a projectile motion problem. And for projectile motion, remember the one thing you have to do is separate the vertical motion from the horizontal motion. In the vertical motion, you're going to use kinematics because you have acceleration. But in the horizontal direction, it's a constant velocity, so you only use v equals delta x over t for the horizontal direction. So let's look at what we have in the vertical direction. One of the biggest mistakes I've noticed that people are still making is the initial velocity. People want to put down the initial velocity of, like in this case, 8.2 meters per second, but that's in the horizontal direction. In the vertical direction, they are not moving when it's first released. So the initial vertical velocity is 0. Since there's no upward motion, let's just define the downward direction as positive to make this a little bit easier. So a is equal to 10 meters per second squared. The delta y is the distance above the water, which is 2.4 meters. And the one thing that connects the vertical with the horizontal motion is time. So you first want to solve for time, and you should get around 0.69 seconds. And once you've got that time, go over here, rearrange for the delta x. That's the thing that we're ultimately looking for. That's this distance. And use the time you just solved for along with that horizontal velocity of 8.2, and you should get a horizontal distance of about 5.7 meters.